We begin by compacting the soil, in this case a regolith simulant, under the shearing box by pressing a small plate of aluminum onto the simulant's surface. We then lower the device into the regolith simulant, using a level to maintain entry direction, until it rests steadily under the weight of the shearing structure. We chose to use regolith simulant to emulate conditions on Mars. The regolith we received is Mojave Martian simulant, with particles smaller than 2 millimeters. Since the weight of the shearing structure only sinks the box partially into the regolith, we load all of our weights onto the load plate, which transmits its load onto the shearing box, to ensure the box is filled with simulant. While the box is under load, we clear away regolith in the shearing direction so that the box is free to move in that direction. We then unload all of the weights. The weights we used are containers filled with exactly 3.5 pounds of regolith simulant each. Then, we load weights equal to the desired normal stress for the test. And finally, lock sliders above the load plate to keep the structure from torquing. The experiment begins by activating the actuator, which slowly extends toward a system of carts, forcing the carts forward along their tracks. This force is directly transmitted through the central beam into the shearing box as our shear force, and is measured by a load cell at the end of the actuator. The shear force pushes the box until the regolith in the shearing plane fails, at which point the force required to move the box lowers. The peak in shear force at failure is monitored by the oscilloscope, which reads out the force on the load cell, and that maximum, along with our applied load, gives us one data point. After several tests at various loads, we can graph a trend line, which we can use to infer the cohesion and friction angle of the regolith simulant sample. In addition, we measure the force output variance with the actuator's displacement, which shows that the force peaks before the actuator begins to move, which is expected from a frictional material following a plastic model, as is the case with granular materials. Comparing that to a force versus time graph, we can observe the matching behavior of the force after the peak, as well as seeing the expected rise in force over time before the peak. While all of our experiments included manual adjustments, most of our project was spent working on designing and building an autonomous device that would perform, for example, the soil clearing step more accurately and automatically. However, our original design for the autonomous device failed due to a mixture of poor quality materials and limited resources, consequences of our very low budget constraints. The device is designed to cover the shearing box while it is lowered into the soil. Then, at the height where the box is filled with soil, a trigger mechanism unlocks two opposing sides of the outer box, allowing mounted springs to clear soil away in the shearing direction. After which the test can be performed under near ideal conditions. After running a number of experiments, we spent some time redesigning the device to ensure that it would function properly and consistently, as well as address the main issues that were encountered in the first generation prototype. 4 vertical aligning rails pass through 2 parallel plates in order to retain the structure's vertical alignment and allow for frictionless movement. To reliably control the depth to which the shearing box submerges, a pneumatic actuator will lower the unit a predetermined distance into the soil. Small hydraulic cylinders are mounted outside the box to open the clearing flaps evenly and smoothly. Then, with weights placed on top of the structure to create a constant normal stress, a horizontal actuator applies a shear force on the box until the soil has sheared. Note that the shearing box sits on the lip of the clearing flap to drive the outer box into the soil. In addition, 4 load cells are mounted inside the shearing box to directly measure the load on the soil. This budget takes into account everything needed for this assembly to be built and used, including machining costs and materials, force transmission systems, measuring equipment, and frame pieces. This project was funded by the Keck Institute for Space Studies.